well, looks like it's noon. We'll go ahead and begin. I didn't have lunch today yet, so I have brought my lunch with me, and we'll talk about that a little bit later. It's extremely nutritious. For those of you at home that didn't see that, I have these large Macy's bags full of various goodies that we're going to talk about in a little bit. And before we move on to reduction, we need to talk just a little bit more about oxidation. You'll recall that last time we talked about taking a primary alcohol. R can be any number of things, but the OH is on a primary carbon. And we talked about using the reagent pyridinium chlorochromate and how that would get us to the aldehyde oxidation state. I think that was the third floor of our oxidation tower, but would not go on to the fourth floor to the carboxylic acid. We mentioned that pyridinium chlorochromate is this organic soluble chromium reagent. The oxidizing agent is chromium. And we drew the mechanism last time. Basically, the oxygen attacks the chromium and chlorine leaves. There are a couple of proton transfer steps. And then the key oxidation step, the place where the magic happened, so to speak, was with this chromate ester intermediate, where you had what we said, and you might not have identified this as such, and that's fine. We're not explaining why this is a good leaving group. You can just accept that it is. The oxygen is at the alpha position attached to the good leaving group. There's a proton at the beta carbon, and so a base, and in this case it's probably Cl minus, comes along and removes that proton. Electrons kick down and the chromium leaving group leaves. This is sort of an E2 style reaction. Now, why is it an oxidation reaction? Because these two electrons that were on oxygen are the ones that attack chromium. They're the ones that are in this oxygen-chromium bond, and in the end, they're the ones that leave with chromium. So we've actually removed electrons from this molecule, which is a definition of oxidation. Okay, questions so far about that reaction? If you look at what changed in the starting material relative to the product, I'm going to highlight the things that aren't there anymore in the product, right? You've got the electrons, this hydrogen, and this hydrogen. And maybe I'll draw that carbon-hydrogen bond just so that we can be clear. So in this oxidation reaction, we lose 2 protons and 2 electrons. So sometimes you'll hear chemists talk about oxidation reactions as dehydrogenation because you're basically losing H2. Now, we're not actually losing a molecule of hydrogen, but we're losing all of the pieces of the molecule of hydrogen. And in biological contexts, enzymes that catalyze oxidation reactions are often called dehydrogenases because they oxidize the molecule, removing 2 electrons and usually 2 protons. Okay? All right. So we wanted to know how then can we go on to the carboxylic acid? And there's an important point here that we need to make. Pyridinium chlorochromate, as I've said, is organic soluble. Typical reagent is dichloromethane, but generally we run this reaction in under anhydrous conditions. There's no water present. And that actually is an important detail. When you write PCC, I'm going to assume you mean it's under anhydrous conditions. There's no water present. Because an interesting, they're having more fun than you guys over there clapping. An interesting thing happens when you try to do this reaction with a chromium reagent in the presence of water. So your text has 2 or 3 different conditions for this reaction. I'm just going to ask you to be responsible for one. This is called the Jones oxidation. Again, you don't have to memorize people's names, but if you end up doing more organic chemistry research, you'll hear people talk about Jones oxidation, and so you just as well know where that came from. This reaction will go all the way to the carboxylic acid. And the mechanism is exactly analogous to what we saw previously for PCC, only instead of attacking the chromium and having a chloride leave, we're going to attack the chromium and break a chromium oxygen pi bond to get a familiar looking intermediate. And from this point on, everything I show you will be exactly the same. From this point on until we get to an aldehyde intermediate, everything's going to be exactly the same as we did for PCC, right? This is, if you go back and you look at your notes for the PCC oxidation, we had this zwitterionic intermediate with a plus charge on the oxygen and a minus charge on the other oxygen. I won't show you the 2 proton transfer steps because those are in the PCC mechanism. 2 proton transfers that generates the familiar chromate ester that I drew up above. And then a base will come in, we'll remove the beta proton, and the leaving group will leave, and then we'll get to the aldehyde. Now, same intermediates, same product. Why is it that we can't stop there for the Jones oxidation? And the reason is that under acidic aqueous conditions, the aldehyde is in equilibrium with another form called the aldehyde hydrate. Now, the equilibrium between aldehyde and aldehyde hydrate is not something that's in your text at this point. That is a 352 reaction. You'll learn the mechanism in 352. It's not hard, and you actually have the tools to understand it now, but there's so much going on that I've decided not to add that to the list of things you have to worry about. If you want to know about it, you can ask me later and I can show you. But the aldehyde will be in equilibrium with the aldehyde hydrate. And what that does is it gives you a chance to do another round of oxidation because now you have an OH group that can be the nucleophile. So I'm skipping a few steps in the mechanism, but you'll eventually get to a chromate ester intermediate that looks like this. Again, the good leaving group here. Again, the oxygen's bonded to the leaving group. There's a beta carbon next door with a proton on it. So a base, probably water in this case, can remove that proton, and leaving group leaves in an E2 style elimination. And that second round of oxidation brings us to the carboxylic acid oxidation state. So there's really not a new mechanism here, aside from the fact that we're pushing arrows a little bit differently to get to the Zwitter ion, which then goes through proton transfers to get the familiar chromate ester. But other than that, getting to the aldehyde is exactly the same. And then the aldehyde is in equilibrium with the aldehyde hydrate, which can then undergo a second round of oxidation to get to the carboxylic acid, which is the final product. Now, let's talk details. Could you just add one equivalent of the chromium reagent and hope to be able to stop at the aldehyde? The answer is no, because as soon as even a little bit of aldehyde forms, it will equilibrate with the hydrate, and then some of that hydrate will go on to react with whatever chromium's left. So in the end, you get a mixture of aldehyde and carboxylic acid anyway. And so if you want to stop at the aldehyde, you use PCC. If you want to go to the carboxylic acid, you can go ahead and do the Jones oxidation under aqueous acidic conditions. And it's this formation of the hydrate that allows you to go through another round of oxidation to get to the carboxylic acid. Okay, questions about that? Yeah?
To clarify, that only works with the primary alcohol?
Does the Jones oxidation only work with a primary alcohol? Yes and no. You can get to the carboxylic acid only from the primary alcohol. Of course, if you wanted to use the Jones oxidation with a secondary alcohol, you can certainly do so. The issue is you have to stop at the, well, you get to the ketone, and then there's nothing else you can do because the ketone actually could form the ketone hydrate, but we've got exactly the same problem here as we had with tertiary alcohols. There's no beta proton to remove, so there's no further reaction. So secondary alcohols can react under Jones oxidation conditions to give you the ketone just fine, same as with PCC, nothing else to see there. It's only the primary alcohol that can go on to the carboxylic acid. What else? Okay, well, we're going to talk a little bit about reduction now. Turn the page. And recall that reduction is our way of taking the stairs or the elevator down from a higher oxidation state to a lower oxidation state. Most of the important reduction reactions you're going to learn you will learn in 352. You're only going to learn a couple today, and they're all going to be related to reducing alkenes and or alkynes. All right, and we'll talk about why you might want to do this in a little bit, but first I want to talk about how you do it. So this is a reaction which we will not learn the mechanism of and which you're not responsible for. I'll tell you a few details, but it may be one that you need to memorize because you won't necessarily have a mechanism to help you. If you take a molecule that's an olefin, I've chosen this dimethyl 1,2-dimethyl cyclohexene for a particular reason. If you expose this to hydrogen in the presence of a catalyst, you can form the syn addition product in which you've added hydrogen across the double bond, replacing the carbon-carbon pi bond and the hydrogen-hydrogen sigma bond with 2 new carbon-hydrogen sigma bonds. And because sigma bonds are more stable than pi bonds, this is downhill in energy, in exothermic. But this is not as easy as putting the olefin in a bottle with hydrogen gas and shaking it up and things go. No, you have to question that we can answer real quickly. This is still in chapter 12, so stay on target for chapter 12, and then I'll give you some more detail in terms of the chapters that we're going to do later. Okay, so you need a catalyst. The reaction is thermodynamically favorable, but it's slow until you add the catalyst. What is the catalyst that we add? It's the transition metal palladium, but we immobilize it on carbon, by which we mean charcoal. Okay. So we haven't talked about, the symbol for palladium is PD. Palladium immobilized on carbon we will abbreviate as palladium/carbon. And you can buy mixtures of palladium and carbon at various different levels of, different percentages of palladium on carbon. A common choice is about 10%. You won't have to say that. The reagent, if you write it just like this, that's good enough. Palladium on carbon is a source of palladium in its 0 oxidation state, so not ionized. But if you look at where palladium is on the periodic table, it's got 8 d electrons. So it's got some space. It's got 8 d electrons and then 2 s electrons, which are sometimes in the d block. Anyway, it's got orbitals that are available to interact with things. So the palladium on carbon catalyst catalyzes this reaction, which we're calling a hydrogenation reaction because we're adding hydrogen across the double bond. This is the opposite of a dehydrogenation or oxidation reaction. I want to give you just a sense for how maybe this reaction occurs. In what we're going to draw, blue circles represent palladium atoms. On a surface, and I'm just randomly putting dots around. I don't actually know what the microscopic structure of palladium immobilized on carbon is. It probably is known, but I don't know it. What happens is that hydrogen reacts with the palladium to generate an intermediate like this. We're not going to do arrow pushing, but basically you can think of electrons from palladium attacking one of these hydrogens and then hydrogen with its electrons attacking another palladium. So the palladium metal breaks the hydrogen-hydrogen bond. Then the olefin comes in, and because the hydrogen is bound to a surface, the olefin has to approach that surface, and only one face of the olefin is reactive. That's the face that's touching the surface. And both hydrogens get delivered to the same face of the olefin at the same time. So that the methyl groups on our olefin end up on the same side and the hydrogens end up on the same side. You're not responsible for this mechanism, and this is just mostly reminding you what happens rather than telling you how it happens, because the detailed discussion of the mechanism is beyond the scope of the text. Okay? Go ahead. When I say it's only reactive on one face, I mean the hydrogens get delivered to just one face of the alkene, not the other. The alkene is planar. It sits down on the surface, and only the part of the alkene that's contacting the surface gets the hydrogens. All right. So this is one case where you can tell that it's been a syn addition. Of course, you can think of lots of cases where you would not be able to tell that it's a syn addition. For example, we're not making any stereocenters here. We're just reducing the double bond from an olefin to an alkane, right? This works with alkynes as well. You can take an alkyne like this, and you can use hydrogen and palladium on carbon to deliver two equivalents of hydrogen across that triple bond to go all the way down to the alkane from the alkyne. And this works pretty well. You may be wondering, could I not just add one equivalent of hydrogen and stop at the alkene? And in general, that doesn't work very well, because as soon as you form the alkene, some of it goes on to react to the alkane. So to avoid getting mixtures of products, we generally add an excess. And I won't ever specify that. I'm just putting it in the notes now so that you know why we go all the way down to the alkane. Questions so far? Right? So now, kind of like we did with PCC, where we were saying, what if you want to stop at the aldehyde versus going to the carboxylic acid? Similarly, we're going to ask with the alkyne, what if you wanted to stop at the alkene instead of going all the way down to the alkane? And there are a couple of ways that we can do this, and they have different stereochemical consequences, and that's important to keep track of. So we can reduce the alkyne to the cis alkene. And our strategy is going to be similar to the palladium on carbon approach. In fact, we're going to use palladium on carbon, but we're going to make it less reactive. And your text describes poisoning the catalyst. Poisoning the catalyst means you add something that makes the catalyst a little bit less reactive. And this was done empirically. There's a name for a commercially available, I think proprietary, or at least used to be, palladium on carbon poisoned catalyst. It's called the Lindlar catalyst, after the name of the person who discovered it. I think one of the poisoners that's added is a little bit of lead carbonate and an amine called quinoline. That's a proprietary mixture, and your text doesn't tell you how or why it works, so I'm going to allow us to all forget that and simply remember that the Lindlar catalyst can take an alkyne and have it stop at the cis olefin. The reason it's the cis olefin is because, as with palladium on carbon above, it's a syn addition of hydrogen at a surface. So you get the cis product because the hydrogens get added to the same side of the alkyne. My penmanship is confusing, actually, so I'm going to write better. Alkane. And because I don't like saying alkene, I'm going to say olefin. All right. But in chemist questions so far, anything you want to ask at that stage? Since chemists like to have ways of doing both diastereomers, then there's another method for making the trans olefin instead of the cis olefin. Okay. And this is to use sodium metal. I'm going to use Na with a 0 to indicate that this is sodium metal in its 0 oxidation state, dissolved in liquid ammonia. You may not know this, but the ammonia you go buy at the grocery store is actually ammonia dissolved in water, sort of some ammonium hydroxide. Ammonia itself is a gas. To make it a liquid, you have to condense it onto something really cold. And so there are chemistry apparati where you can allow ammonia to go into a reaction vessel, have it encounter a very cold surface and drip down into a flask below. It's a colorless liquid. And then you add a chunk of sodium metal to it very carefully and not in the presence of oxygen. And what happens as the sodium metal starts to dissolve in the ammonia is it turns blue, a deep, dark, brilliant blue color. And what's happening there is really sort of bizarre. The sodium metal is going to form sodium cation plus an electron. And what's really, really weird is that that single electron is sort of hydrogen bound to other ammonia molecules. What I'm drawing here is probably not completely accurate, but I want to give you the idea that that single electron is actually shared with and delocalized over many ammonia molecules. And we call this a dissolved electron. Didn't know you could do that. And you didn't know that the color of a dissolved electron was blue, but it is. It's kind of cool. Some people call this the dissolving metal reduction. And if you want to see examples of this, there are some pictures in your text, or you can check YouTube for a dissolving metal reduction, and you can actually see the dark color liquid in the flask that is the ammonia solution of the electron. And these conditions result in the trans olefin. Now the mechanism is shown in your text, but I'm not going to worry about it or hold you responsible for it. The reason you get to the trans olefin is because the reduction occurs stepwise. You deliver an electron to the molecule picks up one proton, you get an intermediate. You deliver another electron to the molecule picks up the other proton, and you selectively get the more stable trans olefin because the mechanism is stepwise. Now, again, I don't feel like it's necessary to know what that mechanism is. It's kind of difficult to rationalize in terms of HOMO and LUMO like we've been doing so far. So we're going to ignore that, and you're welcome to just memorize that the dissolving metal reduction gives you the trans olefin. If you want to have a way to remember that, you can look at the mechanism that's presented in the text, but if you remember that it's stepwise, it's not a syn addition, you just get the more stable alkene. All right. So how might you encounter that in your future? Why, on an exam, of course, he said. So we've done a lot of things where we've done a lot of things with alkenes where stereochemistry mattered. So as an example, imagine taking this alkyne, reducing it with Lindlar's catalyst, then doing the osmium tetroxide dihydroxylation reaction. What would the product be? So that's a predict products question. Well, we would know that, I'm sorry, and I should have put, instead of palladium on carbon, I should have written Lindlar catalyst. We would know that the Lindlar catalyst would give us the cis olefin. then osmium tetroxide does what? Anybody remember? That was last time. Go look it up, it's fine. Ah, good. Some folks from the chat are chiming in. Yes, 2 OH groups and syn addition of those OH groups. All right. So it's okay if you couldn't remember what that reagent does. It won't be okay by the time you get to the exam if you don't remember what that reagent does. So you get the syn diol as the product. Now, I might also have asked you, is there another pathway that works starting from the same alkyne? And let's just say you're going to use sodium and ammonia, the dissolving metal reduction, which is going to get you, after the first step, the trans olefin. Then what would I need to do in steps 2 and 3 to still get that particular alcohol? Yeah, go ahead. Okay, you could use MCPBA, which does what? MCPBA would give you the epoxide from the transalkene. So you'd have this epoxide, I guess, plus it's an enantiomer. And then what would you do after that? Open it up with hydroxide and water. That would lead to the following product, plus it's an enantiomer. And hopefully you can see that by rotating around that carbon-carbon bond, those two are the same product. And I guess in the first reaction, one thing I should have noted as well is that, yeah, you would get both enantiomers because both top and bottom faces of the olefin are the same. Okay, so I can ask this in a couple of different ways. I could do a provide the reagents question where I give you starting material and product, and then I give you various choices. And you better believe I'm going to mix and match Lindlar catalyst with MCPBA, which would give you the other diastereomer, or the dissolving metal reduction with osmium tetroxide, which would give you also the other diastereomer. So be able to follow through the reaction consequences with follow the stereochemical consequences through all of these reactions and be able to use those in a synthesis. All right. Anything else we want to talk about there? Just feeling overwhelmed and you're going to have to catch up later. Is that sort of where we are? Kind of. Okay. This way. I'm waiting for you to catch up. No questions? Well, I'm kind of hungry, so I didn't have my lunch, so but I did bring something. Olive oil for folks at home. That's delicious, right? Crisco pure vegetable oil. This is soybean oil, it says on the back. That's kind of fun. Crisco for folks at home. What else we got in here? Canola oil. I don't actually know what a canola is. I think it's kind of a rapeseed, but I think that is probably a name that discourages purchase, so canola it is. Yes, peanut oil. For fans of Chick-fil-A, we could use this to generate those delicious waffle fries. And, oh, no, that's later. Coconut oil. By the way, this is brought to you by Better Body Foods, which makes me think that this would be even better for me than all of these other oils. And lastly, butter. Who could forget butter, right? What I was not able to get was a big bucket of lard. In my South Texas mission in McAllen and Brownsville and Laredo, you could go to the local grocery store, which then was called H-E-B, and you could buy these big 5-gallon yellow buckets with a red lid of manteca, lard, which you would use to make tamales. The best tamales always were cooked in lard, and you could know a really good tamale because it would have this translucent red grease oozing out of it, and it would make the napkin under it transparent, and that's how you know you had a real good tamale. Miss that stuff. So no, I don't have any manteca here, but we're actually going to talk about fats and oils because the hydrogenation reaction, palladium on carbon, is related to food products that you consume all the time, and it's kind of a fun story. So a little bit of background on biology, and this will be in your notes, so please do not copy this down frantically. Shown here is a triacylglycerol, or sometimes called a triglyceride. The triglyceride has two components. It has a 3-carbon alcohol called glycerol, and then 3 what are called fatty acids. Now, the chemical bond between the alcohol and the fatty acid is called an ester. You've seen esters before. We won't talk about them much until 352. Nevertheless, fats and oils are these triesters where the R group here is a long hydrocarbon chain, usually between 12 and 20 carbons long. Most of the time from biological sources, even numbers of carbons, not odd. And that has to do with the biosynthesis, which you might learn about in 352 or later in biochemistry. The fatty acids come in 2 different varieties, saturated or unsaturated, and that refers to the presence of the double bond, right? So when you now read food labels, you read saturated with what? It's not about like saturating something with, I don't know. It's about all of the carbons being fully saturated with hydrogens, right? So here are a number of examples of the kinds of acids, fatty acids you find in fats and oils. This is not the whole oil or triglyceride. These are just the individual fatty acids. The 12-carbon fully saturated carboxylic acid is called lauric acid. 2, 4, 6, 8, 10, 12. That's what it looks like. Okay, no double bonds. Melting point, I think we talked in chapter 3 about how the longer the hydrocarbon chain is, the higher the melting point is. And you can see as you go for longer and longer chains, the melting points get higher and higher. Even the 12-carbon chain is a solid at room temperature. All right, the unsaturated fatty acids have to have at least one double bond. If they have one, they're called monounsaturated. A lot of nuts have a lot of monounsaturated fatty acids in them. Polyunsaturated means more than one double bond, but the stereochemistry of these double bonds is all, from biological sources, is always cis, never trans. We'll get to trans fatty acids later. And just notice the comparison. Palmitic acid, the saturated 16-carbon chain, has a melting point of 63. Palmitoleic acid, the 16 carbon with a single double bond at carbon 9 and its Z, has a melting point of 0, right? Massive change in melting point by more than 60 degrees. Oleic acid is 18 carbons and also has the same double bond. Oops, Apple Pencil battery as well. Plug it in. And then there are other 18 carbon acids. Linoleic has 2 double bonds. Its melting point is -5 Celsius. 18 carbon linolenic acid has 3 double bonds, -16. And then if you can have a 20 carbon acid with -50 if it's got 4 double bonds. Arachidonic acid compared to the fully saturated 20 carbon arachidic acid, 120 degrees Celsius difference in melting point. By the way, linolenic acid is an example of an omega-3 fatty acid. It's called omega-3 because you've got a cis double bond at carbon 15 of the chain, which is 3 carbons from the end. So the final carbon of any hydrocarbon chain, you know how we've called some things alpha carbon and beta carbon. Sometimes we get lazy with hydrocarbon chains and we don't want to count out letters of the Greek alphabet, so we just say, forget it, we're calling the last carbon omega. Okay? And then omega-3 means 3 atoms from the end and you've got a double bond. And these are, in some cases, associated with better cardiovascular outcomes, diets that are rich in omega-3 fatty acids. Though it's difficult to tell in food how much is legitimate evidence and how much is mostly marketing. For example, you can buy eggs that are enriched in omega-3 fatty acids, presumably because they feed the chickens a bunch of stuff that has omega-3 fatty acids in it. But this isn't a food science class, and I don't know the food science literature. But when you hear omega-3, forever now in your life, I want you to be thinking, yes, the cis double bond on the 3rd carbon from the end. And I want you to say that to people, like when you're in the grocery store. Oh, look, these are omega-3 eggs. Yes, the cis double bond, 3 carbons from the end. All right, so I thought it might be interesting. You can see the different physical properties of these oils that I've got in front of you. I've taken pictures of them for folks at home, and I'm going to get the Apple Pencil again. So you've got vegetable oil here. This is soybean oil, canola oil, peanut oil, olive oil, all liquids. Coconut oil, solid. Butter, solid. So let's look at the composition of their fatty acids and see whether that makes sense. I've listed here fatty acids according to their number of carbons. Saturated fatty acids are on top. Unsaturated are on the bottom. Number of carbons is here, and since the unsaturated ones we'll be looking at all have the same number of carbons, oleic has 1 double bond, linoleic has 2, linolenic has 3. If you look at the ones that are liquids, they are mostly unsaturated fatty acids and only have a small number of saturated fatty acids. In contrast, coconut oil, which is a solid, only has a very small amount of unsaturated fatty acids and a huge amount of saturated fatty acids, in particular the 12 carbon chain. That's reflected in the nutritional label. Just compare coconut oil with olive oil. Both have 14 grams of fat in a serving. Olive oil only has 2 grams of saturated fat, 11 grams of monounsaturated fat, and it's exactly backwards for coconut oil. And going back up to the fatty acid temperatures, that's why coconut oil is a solid, because all the hydrocarbons are saturated, and the saturated hydrocarbons pack better against each other and generate bigger van der Waals forces. Butter is also a solid, though butter has a substantial amount of the 18 carbon 1 double bond, but still mostly fully saturated fatty acids. Now, suppose So those are some sources of fats and oils that are available from natural sources. But what then is this weird Crisco? Open it up. It is clearly a solid. Don't you just want to stick your finger in that and take out a slog and just slurp that thing down? What is Crisco? If we go in and look at the label, it says soybean oil, fully hydrogenated palm oil. What is the fully hydrogenated part? Well, presumably at some point somebody decided they wanted to use a vegetable oil product because that's cheaper than getting cows to make butter, but they wanted it to be a solid. So they said, this is easy. Let's take the triacylglycerol from vegetable oil that has all these double bonds, and then let's reduce them with palladium and on carbon and hydrogen. I don't actually know what the metal catalyst is, but the process is hydrogenation, and it does involve a metal catalyst. So they could get this to become a solid, and that was great. But there were a couple of challenges associated with that. The other reason you would want to, and we'll talk about that in a second, the other reason you would want to hydrogenate oils is because the double bonds in fats and oils are subject to something called oxidation. We'll talk about a similar reaction in the chapter on radicals, but basically these carbons that are allyl to double bonds are easily modified by molecular oxygen to form weird peroxides and alcohols. And those don't taste very good, nor do they smell very good. So some of you may have carried around a little vial of olive oil in your mission to various hot climates, and maybe you never had occasion to use it. Maybe after you came home, you opened up that bottle and probably it smelled terrible. That's because the oxidation reaction happened. In fact, this allows me to tell you about the rancid tostadas of 2016. These are not actually from 2016. I bought them today, but one week, we go to my mom and dad's house every other week for Sunday dinner. And Mom plans out her Sunday dinners in the same way that a general plans out a battlefield. There are contingency plans. There's always more than enough food so that if there's someone she doesn't have a lot of confidence in terms of their ability to do stuff well, and so there's always a backup plan. In this case, it was great because we were supposed to bring the tostada shells, and I pulled the bag of tostada shells out of our pantry. It had been there a while, but what could possibly go wrong? I took it to Mom's house. We opened the thing up. People started eating, and they were like, what is that? And the tostada shells were old enough that the oil had gone rancid. Why is that even possible? Well, look at the nutritional label for the tostada. Lots of unsaturated fats. And those get oxidized and they smell bad. Fortunately, Mom had a brand new bag of tostadas in her pantry, suggesting that even though she had assigned me to do it, she was planning on me to fail. Which now, I have my own teenagers now, and I totally get that. So one of the reasons why you'd want to hydrogenate fats and oils is because it removes the double bond and the oxidation can't happen and it can't go rancid anymore. So that's why people used to do hydrogenation. Now we're going to go back to that Crisco label, and it says fully hydrogenated palm oil. It used to be you would get products that were partially hydrogenated. They don't sell those anymore. And the reason is that the hydrogenation process is somewhat reversible, and if you don't do it completely, you can generate a little bit of the trans fatty acid, which is associated with negative cardiovascular outcomes. Margarine, used to be hydrogenated. They've got some other methods now for making vegetable oil a solid. But notice they're going way out of their way to tell you there are 0 grams of trans fat per serving, where 0 grams means 500 milligrams or less. So it doesn't actually mean 0, it just means less than 1. And so when you see products that are advertised this way, That's part of the deal. Now, we're running out of time. I'll mention this next time. I have here Skippy, which is smooth and homogeneous, and Adam's 100% natural peanut butter, which you can't see, but if you want to come up after class, there's a layer of oil at the top of this thing, which the real professionals break open the bottle and drink the oil first, and then they eat the solids. No, actually, you're supposed to stir it. There's a reason why this is homogeneous and solid and this is a liquid. It has to do with hydrogenation, and we'll mention it next time.